In this video, we're going to talk about another way to test extrema values to see whether they are relative maximums or relative minimums. Okay, the test we're going to use is called the second derivative test for extrema. This only works for some types of critical numbers, so you can't do this for every type of critical number, and sometimes it will fail even for critical numbers where it might work. But if it does work, it can be a lot faster. So let's figure out what this test looks like. So consider this function, and this is the one from a previous video. So notice that at x equals -3 and at x equals -1, okay, we have critical numbers. Okay, so the slope here is 0. So that means that f prime of -3 is 0. And f prime of -1 is also 0. Okay, so x equals -1 and -3 are critical numbers for this graph. Okay, now from the graph we can see that at x equals -3, okay, y equals 1 is a relative maximum. Okay, and y equals -3, which is at x equals -1, is a relative minimum. Okay, now we can actually use the concavity to figure out for these ones that they were a relative max or relative min. So even if we didn't have the graph. So notice, what would it be? What would the second derivative at -3 be? So we can't maybe figure out the exact value, but do we think it's going to be positive or negative? So to tell, you want to think about the graph. Okay, so on this part of the graph, so specifically at -3, is it concave up or concave down? Because that's how we can tell whether the second derivative is positive or negative. So if we think about dumping water on the top, okay, it's going to roll off. Right? It's not going to hold the water. Also, the tangent line I drew lies above the graph. Okay, both of these are indications that it's concave down on this interval. So that means that f prime of -3 is going to be less than 0. It's going to be negative. So in fact, it goes all the way until -2, I think, that it's concave down. So because it's concave down, the second derivative is going to be negative. Okay, now when you have a critical number with a negative second derivative, what that actually tells you is that it has to be the top of some mountain, the peak. Okay, so it's a critical number with a derivative of 0. Okay, and when it's concave down, it means that it can't be the bottom, it has to be the top. Okay, so from this, using the second derivative test, which I'm going to tell you, we should be able to conclude that x equals -3 has a relative maximum. Now, for -1, the second derivative here is positive, because on this interval, the graph is concave up. Okay, now when you have a slope, a critical number with derivative 0, and the second derivative positive, that tells you that it has to be the bottom of some valley, so therefore a relative minimum. Okay, so that's what's going on in this second derivative test. So here's the statement. So let f is twice differentiable. So the second derivative exists on some open interval containing the point C, okay, except maybe at C itself. And the first derivative at C is 0. Okay, then if f double prime at C is bigger than 0, okay, so that means that it's concave up there, then we say that the y value at C is a relative minimum for the graph. Okay, so it means that, so at C is a critical number, and it's concave up, so it has to be the bottom of some valley. Okay, now if it is, the second derivative is less than 0, that means that it's concave down. Okay, so then f of c, the y value at c, is a relative maximum. Okay, so here, so if this is c, it's a critical number, a nice critical number, okay, and it's concave down, so it has to be the peak of some mountain. Now, if the second derivative is 0 at c, or the first derivative does not exist, or the second derivative does not exist, then we say that the test fails. Oops. Okay, so what that means is it tells us nothing. So it does not tell us that it's neither. Okay, it doesn't tell us that it's not a relative max or min. It just tells us that this test didn't work. Okay, so to classify these types, you are going to have to use the first derivative test, which is the increasing, decreasing one, which never fails. Okay, so just to give you a couple of examples here. Okay, so if my graph looks like this, okay, so this would be a critical number, but it's a vertical tangent, so the derivative doesn't exist. And then we get no max min. Okay, but it could also be that it looks something like that. So here this first and second derivative won't exist here, but here we actually get a relative min. Okay, so that it could be that you get a relative min even though the test fails. It could be that it's neither. It could be anything. So you can't conclude anything. So just to remind you, this test only applies to critical points or critical numbers c, for which the first derivative at c equals 0. Okay, so you cannot use it if the first derivative at c does not exist. So if it's that type of critical number, you can't use this test. And our test fails if the second derivative is 0 or does not exist. Okay, so then it was sort of pointless. So it was a waste of time. It told you nothing. So because of that, this test is not used so often, but it can be a lot faster. Okay, so let's just do an example. Okay, so suppose we have this function. So f of x is x cubed plus 6x squared plus 9x plus 1. So we want to determine all the critical points, the inflection points, and concavity for the function. And then we're going to use the concavity to classify the critical numbers or critical points, if possible. So to find the critical numbers, we want to take the first derivative. So that's going to be 3x squared plus 12x plus 9, okay, which is 3x squared plus 4x plus 3, which then factors as x plus 3 times x plus 1. Okay, so that's our first derivative. So if we set this equal to 0, we're going to get that x plus 3 is 0 or x plus 1 is 0, which means that we have x equals negative 3 or x equals negative 1. Okay, so these are our critical numbers. Now we should also think about where the derivative does not exist. We want to get in the habit of that. Okay, but here it always exists because it's a polynomial. Okay, now we also want to think about the second derivative. So that's going to be 6x plus 12. Okay, so then if we think about where the second derivative is 0, that's 6x plus 12 equals 0, which means that x is equal to negative 12 over 6, or negative 2. Okay, and then f double prime of x, where does it not exist? Okay, well, it always exists, so we don't have to worry about that. Okay, so this x equals negative 2. This is a possible inflection number. Okay, so we found all of our important numbers. So we want to first figure out where the function is concave up and concave down. Okay, so we can make our number line with x equals negative 2. Okay, so I'm just going to have two intervals that I need to check. So let's say we check negative 3. So if I plug in f double prime of negative 3, that's 6 times negative 3 plus 12. That's going to be negative 6. So it's negative, so it's down like a frown, so concave down. If I'm bigger than negative 2, maybe I'm 0. That's going to be 6 times 0 plus 12, so that's 12. So it's positive, which means it's happy, or concave up. Okay, that means that this point where it changes is a point of inflection. Okay, so we want all the inflection numbers, the inflection points, so we're going to want to find the y value at x equals negative 2. Okay, so we can start. So we know that it's concave up on the interval from negative 2 to infinity. And oops, it's concave down on the interval from negative infinity to negative 2. Okay, so we know the concavity. Oops, that was part of what we wanted. And we know that there's an inflection point. So let's find f of negative 2. So that's where we want to use the original function. So it's negative 2 cubed plus 6 times negative 2 squared plus 9 times negative 2 plus 1. So this is negative 8 plus 24 minus 18 plus 1. So I think that's 25 minus 26. So I think I get minus 1. Okay, so that means we have a point of inflection is at the point negative 2, negative 1. Okay, so we know that. Now, we also want to test our critical numbers. Okay, and we want to use concavity to do it. So we want to try to use a second derivative test. Okay, so we're going to use the second derivative test to classify x equals negative 3 and x equals negative 1. So what we do, these are both, maybe I should point out, so remember that f prime of negative 3 was 0, as was f prime of negative 1. Okay, so because they're equal to 0, the second derivative test applies. Okay, so these are critical numbers where it's possible to use the second derivative test. So what we want to do is plug the number -3 into the second derivative. Now I believe we already tested -3, so we got -6. Okay, so this is less than 0. So the second derivative test says this is concave down, which means that it has to be the top of some peak. So that means that, maybe I'll just say, so f of -3, so the y value at -3 is a relative maximum. Okay, now if we test at -1, which I did not do, but if I plug in -1, it's 6 times -1 plus 12, so positive 6. So that's positive. So when the second derivative is positive, means it's concave up. And for the second derivative test, we can conclude that f of -1, the y value, is a relative minimum. Okay, so we're going to have a relative minimum at the point -1, and the y value is -3, I think. And there's going to be a relative maximum at -3, and the y value is +1. Okay, we can conclude that from the second derivative test. Now, just to point out, so to find, oops, I didn't want that. So to find this -3, okay, -3 is actually f of -1. So if I plug in -1 into the function, I get -3, and f of this 1 here is actually f of -3. So if I plug in -3, I get +1. So the y values are found using the original function. Now, if you want to verify, if you don't believe the second derivative test, you can verify these relative extrema, the classifications for them, using the first derivative test. So if you determine the increasing decreasingness, so your table should look like it splits at -3 and -1. And what you're going to get is that it increases and then decreases and then increases. Okay, so you'll see that this is going to be a max and this is going to be a min. Okay, you'll get the same conclusions. So you can check using that method if you'd like. It's good practice.